I want to continue our discussion. I'm going to turn down the volume just a little bit, and I guess I should actually grab a mic here. I want to continue our discussion of various carbonyl reactions and specifically pick up sort of where we left off talking about the Aldol reaction, the Aldol condensation reaction. And I want to talk about Aldol reaction where we have a couple of two different components, what's called a crossed Aldol reaction. Your textbook brings up, and I think it's reasonable because I think for beginning students, although intramolecular aldol is no different than intermolecular aldol, I think people often have a chance of getting confused or a chance to find it confusing. And so I want to talk about intramolecular aldol reactions. And then we're going to talk about Robinson annulation, which is going to put some of this together. I guess we'll also along the way talk about the Michael reaction. So I'll mention that. All right, so where we were talking last time, we started talking about the Aldol reaction, and specifically, I was talking about at the end, the Aldol reaction with dehydration. So remember, the Aldol reaction is where a ketone or aldehyde or ester generates an enolate, and that enolate reacts with a ketone or aldehyde. And if you have the two as the same molecule, it's kind of simple. You don't have any choices. You'll have, say, a ketone like propiophenone generating an enolate with base like sodium hydroxide and water, and then reacting with another molecule of the ketone. And at the very end, I pointed out that if you have, typically if you warm the reaction up, you can end up losing water. And so I think the last example I provided was two molecules of propiophenone coming together. Like so. There you have a dehydration. So I presume you've already seen this, but I think this is a good starting point now for the crossed Aldol reaction. Not going to capitalize since Aldol isn't anybody's name. If I'm just writing things out as words, I would simply write it as a lowercase aldol. So if you imagine the conundrum, if we had two different ketones or aldehydes, let's say just for the simplest example, we took propanol and we took butanol, and we imagine mixing them together under these same type of conditions that promote aldol reaction with hydration, namely aqueous base or base, aqueous sodium hydroxide in water, or alcoholic sodium ethoxide in ethanol. And we heated this up. Now, by way of analogy, you'd say, oh, this is going to be very confusing. These molecules could come together in four possible combinations. In other words, we could have propionaldehyde, propanol generating an enolate and reacting with butanol, We could have butanal generating an enolate reacting with propanal. We could have propanal generating an enolate and reacting with itself. We could have butanal generating an enolate and reacting with itself. So in other words, we would end up with a mixture of products. And I'll just sort of point out for your notes 4 ways of coming together. But if we choose our carbonyl compound and our aldehyde wisely, then we won't necessarily have a mixture of products, or at least not a horrendous mixture of products. So imagine for a moment that I take acetone, and imagine for a moment that I take benzaldehyde. So now we have a little bit of a different situation, right? Acetone is a ketone. Benzaldehyde is not only an aldehyde, but it's a non-enolizable aldehyde. In other words, there are no alpha protons. So the ketone can generate an enolate but the aldehyde can't generate an enolate. And the situation's even a little bit more cut and dried than that. Ketones are less electrophilic than aldehydes. So if we generate a ketone enolate and it has a choice, it's going to react with the aldehyde. In other words, the aldehyde is going to react far faster with acetone enolate. Benzaldehyde is going to react far faster with acetone enolate than is acetone. And so we actually will get a single product out of this reaction. So again, if I say, all right, we'll use sort of my favorite conditions for an aldol reaction with dehydration, namely aqueous base and warming the reaction mixture up. Now we'll get a single aldol product like so. In other words, this reaction is going to go by way of, and I'm not going to write the whole mechanism, by way of base generating an equilibrium concentration of acetone enolate. Remember, the pKa of H2O of water is 15.7. We'll just call that 16. The pKa of acetone is about 20. So the equilibrium between hydroxide anion and acetone lies way to the left, but you generate a small concentration of acetone enolate, about 1 part in 10 to the 4. In other words, 10 to the -4 equilibrium constant. And that's enough to undergo reaction with the aldehyde. So that you generate some enolate, it reacts, you generate more enolate, it reacts more. And under these conditions, if you remember us thinking about mechanism last time, you can get a dehydration reaction. We wrote this out where you protonate your aldolate, then you further generate another enolate, and the enolate kicks out OH minus. So I don't want to go over that, but you can review your notes. Okay, so that enolate here goes ahead, and in the first step of this reaction, I'm not going to again write the whole mechanism. In the first step of the reaction, the enolate attacks the acetaldehyde, and that's the preferred reaction over, or attacks the benzaldehyde rather, and that's the preferred reaction over, say, attacking another molecule of acetone. So we call this a cross-Staldol reaction. And it specifically is because we have two components. We've mixed everything all together, and yet, shall we say, the molecules know how to react. Remember, I started us off with the aldol reaction talking about an LDA aldol. And I love an LDA aldol reaction because we have control. You say, well, I want you to become the enolate and you to become the reactive aldehyde or the reactive partner, and you have that control. But if you're mixing everything together without that very strong base, without LDA, pKa of the conjugate acid 40, you don't have that level of control. And of course, we could have done this reaction in two steps. We could have gone ahead and generated the enolate of acetone with LDA, added benzaldehyde, done a workup that would have gotten us to the beta hydroxy carbonyl compound. And then in the second step, either with base or acid, done a dehydration reaction. But here we've mixed everything together all at once, and we call it a cross-Staldol reaction. Questions or thoughts at this point? Yeah.
So for the alkene, would that always be E?
Great question. Would the alkene always be E? And the short answer is, in some cases, yes. In some cases, no. But in this case, yes. If the two groups are bulky, particularly a phenyl group, and also under equilibrating conditions, which these are, you will get the trans product essentially exclusively, 90 plus 95, 99 to 1. So you'll get very little of the cis product. Had we, for example, had a little bit more choice, like had we used this component, had we used 3-pentanone and benzaldehyde again, you probably wouldn't have had as much selectivity. So for example, you probably still would have had the trans product, the E product, as the major product, but you probably would have had a small but significant amount of the other stereoisomer of the Z stereoisomer. So here, I would say in this case, this would probably be major and minor with, maybe it would be 4-to-1 ratio or something to that effect. Good question, and I think a really thoughtful question. The other point I guess I should make is these types of dehydration reactions can occur with both aromatic aldehydes, right? Benzaldehydes and aromatic aldehyde, but they also can occur with aliphatic aldehydes. Nevertheless, with aromatic aldehydes, they tend to be particularly prevalent. In other words, it would be very hard to stop this first reaction under these conditions. It would be hard to stop the reaction over at the beta hydroxy carbonyl stage under these types of equilibrating conditions. Other questions? Oh, thank you for them over there. Yeah. Other questions? Let's take one last example of a cross-Staldol reaction. It really is a very versatile reaction, and I want to give you a feeling for the versatility. So I'm going to take diethylmalonate, and which is a diester we've already talked about. It's a relatively acidic alpha proton, pK of about 13, and we'll take this aldehyde. So furan is another aromatic molecule, and although you don't see it nearly as often as benzene, this molecule here, furanaldehyde or furfural, it's kind of a fun name to pronounce, furfural is just another aromatic aldehyde. And just like benzaldehyde, it's not enolizable. Now, I got a very good question by email from a student about knowing the right base to use or how particular molecules tend to react. So if I were choosing a base for a reaction of an ethyl ester, I would invariably choose sodium ethoxide in ethanol if I weren't doing an LDA reaction, because the ethoxide can also attack the carbonyl, and that reaction will be degenerate in the case of ethoxide. In other words, if ethoxide attacks the carboethoxy group and we do an additional elimination, we don't generate a different ester. We don't hydrolyze. If I'd used sodium methoxide in methanol, we would have generated some methyl ester, but I've chosen sodium ethoxide in ethanol, so that doesn't occur. Sodium hydroxide would be hydrolyzing the ester groups. And so we're really set up at this point for just aldol reaction occurring. And as I said, I wanted to show you sort of the diversity of different products that can be generated from this very versatile aldol reaction. So here we've done an aldol reaction or an aldol reaction with dehydration, also referred to as a condensation. So I can say, we can also call this an aldol condensation. Condensation is another way of saying you lose something, and we've lost a molecule of water here. In other words, if you write a balanced chemical equation, the base is only a catalyst here, but one molecule of diethyl malonate reacts with one molecule of furfural to give you one molecule of the alpha beta unsaturated carbonyl compound, plus one molecule of water. And that's sort of the hallmark of what's called a condensation reaction. So any thoughts or questions at this point? Yeah. Over here. Well, in this case, remember, first of all, of course, there are no other significantly acidic protons in the molecule, but your textbook has other examples. For example, ethyl aceto. Well, we've used ethyl acetoacetate, and you're going to see ethyl acetoacetate again. So ethyl acetoacetate, yes, I mean, it does react in the middle, but there's a very obvious reason, right? The proton in the middle is about 11 pKa, and the proton off of the carbonyl is about 20 pKa value. So the more acidic protons react. Here we don't have a choice, but even if we did, again, with pKa of about 13, those protons are substantially acidic. Now, remember my rules of thumb of pKa's. If the pK of ethanol is 16 and the pKa of diethyl malonate is 13, that equilibrium lies way to the right when you mix sodium ethoxide and diethyl malonate. That equilibrium lies 1,000-fold, 10 to the third, to the right. So basically, you quantitatively generate the enolate of diethyl malonate here with sodium ethoxide and ethanol. Yeah. why I don't use heat. So good question. It wouldn't hurt. It isn't necessary becomes the real thing. So the heat is key to the dehydration part of the reaction. And so we get over, and I'm hoping you can get yourself over to the aldol product. In other words, I'm hoping that at this point, you can go ahead and say, okay, I can picture in my mind's eye, the sodium ethoxide deprotonates the diethyl malonate, we generate the enolate. The enolate attacks the aldehyde, we generate the aldolate, the oxyanion. The oxyanion picks up a proton, the aldolate picks up a proton from ethanol to get us over to here. So now this proton here, the one that I'm pointing at, the one that's between the two carboethoxy groups, is still very acidic. It gets quantitatively deprotonated by sodium ethoxide at this point. And I'm going to do what I don't like to do. I always like to write a different resonance structure, but just to help you see it, I'll go ahead and show you this resonance structure. So you pull that proton off, you generate an enolate, and then we're well set up for elimination, kicking out hydroxide. So this reaction really goes quite like a shot. So it wouldn't hurt to heat this reaction mixture, but you probably wouldn't have to drive it. That's a great question from the chat. All right, I want to talk now about what happens when you have the two components for an aldol reaction in the same molecule. And we'll start with a reasonably simple example. And a general rule of thumb is that 5 and 6 membered rings generally form pretty easily. 3 and 4, not so much because they're strained, right? The ring strain of cyclopropane and cyclobutane are close to 30 kilocalories per mole, high 20s. 7-membered rings are also a little bit strained. So generally, given a choice, a molecule is going to form a 5 or 6-membered ring. So if we take this ketone is hexane 2,5-dione, and we mix it with sodium, we cook it up with sodium hydroxide and heat it up, we get an intramolecular aldol reaction, and the product of the reaction is like so. Now, these are equilibrating conditions. So you look at this molecule, there are 2 types of enolate that can form. There's the enolate off the methyl group, there's the enolate off the methylene group. The molecule is symmetrical. But only the enolate off of the methyl group can undergo an intramolecular reaction to form a 5-membered ring. The enolate off a methylene group could undergo an intramolecular reaction to form a strained 3-membered ring, but that wouldn't be nearly as good. So in these types of equilibrating base conditions, protons come on, protons go off, protons come on, protons go off. You have some equilibrium concentration of the enolate on the methyl side. That enolate is now poised to attack that carbonyl group intramolecularly, like so. And then it almost helps to count your way around if you want a little bit of a sort of cheat here to see where we're headed. You could say, okay, 1, 2, 3, 4, 5, and you could say, okay, what does that do? And when you, with a little bit of practice, you'd start to recognize, okay, what that's doing here is getting ourselves over to this aldolate. And you could say, all right, where do I go in my mapping? 1, 2, this is atom 3, this is atom 4, and this is atom 5. And you can see how these came together. Whoops. Eventually, I think you'll become good enough, even without mapping the atoms, just to see, okay, I'm forming a 5-membered ring, and see your way around. So continuing then with what's happening. So this reaction, we have sort of an equilibrium reaction here. Of course, we have an equilibrium reaction with hydroxide to generate the enolate. We have an equilibrium reaction with the enolate and water, or the aldolate and water, to pick up a proton. Like so. That, of course, generates more hydroxide. We have equilibria, protons go on, protons go off, all acidic positions. We generate some equilibrium concentration of this enolate, and this enolate has a productive pathway to dehydration, like so. To take us to our aldol product. Thoughts or questions? I think one of the skills that we try to cultivate is thinking backwards. In other words, being able to look at, and I think probably Maya and Jackson and Matt do this all the time in their synthetic work, look at a molecule and say, where would that come from? It's almost a puzzle, and often it's an inherent research problem. Jackson later today is going to be making a presentation in a graduate course on a synthesis of a very complex molecule, and his presentation is going to feature this type of retrosynthetic thinking. So when you look at a molecule like this and you say, oh, it's an alpha beta unsaturated carbonyl compound. I know where alpha beta unsaturated carbonyl compounds can come from. They can come from aldol reactions, specifically aldol reactions with hydration. And so you can apply this sort of thinking backwards or retrosynthetic analysis to say, oh, I know we form the bond between the alpha and beta carbon, right? This is the alpha carbon. That's the beta carbon. And that means that we can take this molecule apart like that. In other words, that molecule, the molecule on the left, the alpha beta unsaturated carbonyl compound, can come from the molecule on the right, which if we just unwrap it, we say, oh, okay, wait a second, that's just pentane diol, just 2,5-pentane diol. So as I said, 5- and 6-membered rings tend to form in an intramolecular aldol reaction. So if I go from 2,5-pentane dione to 2,6-heptane dione and subject it to the same type of conditions, sodium hydroxide and water with a little bit of heat, it shouldn't surprise us by analogy that we get the 6-membered ring. In other words, there's just one more carbon connecting the two. In other words, now instead of getting a cyclopentenone product, we get a cyclohexenone product. And if we take this one step further and go to octanedione, now you look at this and you say, okay, well, 7-membered rings aren't that good at forming. They're a little bit more strained. We're under equilibrating conditions. Maybe there's a different enolate that can be generated. And if we think about that and say, oh, okay, well, remember, protons go on, protons go off. You get all different possible enolates, but some of those enolates are going to react productively. Some won't. If you look at the position, the methylene group, and you say, oh, okay, wait a second, this side is just 5 carbons away from the carbonyl group, you say, okay, I see a path forward to a 5-membered ring forming. So this pathway is likely to be the most productive pathway. I'll just write ditto marks to say same conditions. And if you go through the same type of thinking and look at how the bonds form, you get yourself over to this aldol product with dehydration. Thoughts or questions? All right, so I want to switch gears at this point and start talking about alpha beta unsaturated carbonyl compounds, and particularly the Michael addition reaction. So alpha beta unsaturated carbonyl compounds have their own reactivity that has a couple of possibilities. So if I have sort of a generic alpha beta unsaturated carbonyl compound, I'll just say an alpha beta unsaturated carbonyl compound. Not to mean a specific one. It's a carbonyl compound, so it's electrophilic at the carbonyl compound, at the carbonyl group. But the beta position is also electrophilic and we can think about that as follows. So if we look at this compound, this sort of archetype of an alpha beta unsaturated carbonyl compound, you'd say, okay, this is what I would call the major resonance structure. This structure here is most representative of how I think about the molecule. But we've already talked a little bit about carbonyl compounds and said there's a minor resonance structure that helps us think about the reactivity of the carbonyl group. Oxygen's more electronegative than carbon. That means the double bond between oxygen and carbon is not share and share alike. It's share but unequally. In other words, we have a minor resonance structure that really helps explain the electrophilicity of the carbonyl group. But if we look at this molecule and we look at the double bond and we think about resonance, we can also recognize the fact that there's a positive charge as well at the beta carbon. And that gives us another minor resonance structure. And, if I had to kind of paint a picture of how much each of these structures might contribute, I might say, oh, maybe it's like 80% of the structure on the left and like 10% of the structure in the middle and 10% of the structure on the right. In other words, you could say, all right, there's a partial positive charge at the alpha carbon, a partial, or at the carbonyl compound, there's a carbonyl carbon, there's a partial positive charge at the beta carbon. It's not a full charge, it's not even half a charge, it's just a fraction of a positive charge at each of those positions. And for that reason, nucleophiles can add to the beta position. So if I wanted to give you sort of a rule of thumb, I would say strongly basic nucleophiles tend to add at the carbonyl carbon. And for the purposes of this discussion, or the purposes of at least how I organize things in my head, I would say a strongly basic nucleophile is a nucleophile for which the pKa of the conjugate acid is greater than or equal to about 25. So our NUH has a pKa greater than or equal to 25. What do I mean? Okay, take a simple example. Methyl lithium, right? Methyl, we think of it as a methyl nucleophile or a methyl anion. The pKa of methane is 50. If I treat this alpha beta unsaturated carbonyl compound with methyl lithium, the methyl lithium is going to add to the carbonyl carbon. Another example, ethyl acetate. If I make the enolate of ethyl acetate has a pK of about 25. That enolate is likely to add predominantly to the carbonyl carbon. Now, at the other end of my rule of thumb, I would say moderately basic nucleophiles tend to add at the beta carbon. And by moderately basic nucleophiles, I mean nucleophiles where the pKa is, say, less than or equal to 15. So the 1,3-dicarbonyl compounds we've been talking about are great examples of this. If I take ethyl acetoacetate, right, pKa of the ethyl acetoacetate is about 11. And I take cyclohexenone, an alpha beta unsaturated carbonyl compound, and I mix them up with some sodium ethoxide in ethanol. Remember, I try to match the ester group to the alcohol. I wouldn't want to use sodium hydroxide because it might hydrolyze the ethyl acetoacetate. I wouldn't want to use sodium methoxide in methanol because it might transesterify. And so if I mix up my ethyl acetoacetate with sodium ethoxide and ethanol and cyclohexenone, the product of this reaction corresponds to the reaction of the enolate at the beta carbon like so. And this is an example of what's called a Michael addition or Michael reaction. And that was why when I was annotating my title to today's lecture, I realized I had forgotten to mention the Michael addition reaction. So, okay, this is a little bit of a mouthful to see the first time. So let's break this down. So sodium ethoxide is able to deprotonate the ethyl acetoacetate. I'll write this just, I'm not going to do a full sort of arrow pushing mechanism, but I want to walk us through the various steps. So, okay, my preferred way of writing an enolate is with the negative charge on the oxygen. I talked about that before. So sodium ethoxide can deprotonate the ethyl acetoacetate to generate the enolate. And remember, that equilibrium lies about 10 to the third to the right. So you can write it as an equilibrium, but basically I take 1 mole of sodium ethoxide and 1 mole of ethyl acetoacetate, and I get essentially 1 mole of the enolate. That enolate is able to undergo a 1,4 addition or Michael addition reaction like so. Here's our enolate. We can push electrons down, push electrons off the beta carbon, or off the alpha carbon. We attack the beta carbon. That pushes electrons up. That pushes electrons onto the oxygen. The overall result, if we trace our electrons at this point, is we now have a single bond to the oxygen that used to be a carbonyl. We have a double bond here. In other words, we have an enolate. We now have a carbon-carbon bond between what used to be ethyl acetoacetate and what used to be cyclohexenone. And at this point, our enolate can protonate. Like so, to generate more ethoxide. Technically, if I used a mole of sodium ethoxide, I would then deprotonate this alpha carbon over here. I probably shouldn't leave a mark on my page, but I would deprotonate that alpha carbon there, and we would in workup protonate it. Anyway, this is the basic thing that happens in a Michael reaction. So very much like the Aldol reactions that we looked at, with the big exception that attack is occurring at the beta carbon. Questions or thoughts? Yeah. Haha. What about the gap? It depends. And so the gap, of course, absolutely great question. So the gap we're talking about let's say the enolate of acetone, right? Acetone pKa on the order of 20 for a ketone enolate. It depends. Under some conditions, acetone enolates, I used LDA to generate the enolate of acetone or a related ketone. Under some conditions, that enolate would add to the carbonyl group. Under some conditions, it would add to the beta carbon. If, for example, I generated an enolate of acetone or a related ketone at -78 degrees, and then mixed it with cyclohexanone at -78 degrees, and added an acid, let's say ammonium chloride, to the cold reaction mixture, I would get predominantly addition to the carbonyl group. If I let that reaction mixture warm up or did that reaction under equilibrating conditions like sodium ethoxide in ethanol, we would get predominantly addition to the beta carbon. And in this case, we would refer to the product that attacked at the carbonyl group as a kinetic product because it forms more easily, but the product at the beta carbon as the thermodynamic product because it's generally more thermodynamically stable. We're going to see an example of this in just a moment when I take us to the Robinson annulation, where we'll be seeing lots of ketones reacting at the beta position of 1,3-dicarbonyl compounds. Other questions? Great question. All right, let's take a look now at our product. And I want to view it through a fresh set of eyes. So I'm going to rewrite it. All right, so here's the product that we wrote from our Michael reaction. This is a 1,5-dicarbonyl compound. In other words, just like ethyl acetoacetate is a 1,3-dicarbonyl compound where the carbons are 3, the carbonyl groups are 3 carbons apart. Here we have a 5-carbon relationship between the 2 carbons. And in thinking about this, this is very useful because it gives us an idea of retrosynthetic analysis. In other words, we can look at a 1,5-dicarbonyl compound and say, if we break the bond between the 3 and the 4 carbon, we can see how that molecule can form. In other words, that molecule forms by way of a Michael addition. And that's a way of taking these apart in your mind's eye, of seeing how 1,5-dicarbonyl compounds can form. So in thinking more broadly, we've been doing a lot right now in this area of retrosynthetic analysis. And I want to write down all the different things that we've learned, or at least in one case, 2 cases are about to learn. Okay, We've learned, for example, that a beta hydroxycarbonyl compound can be formed by an aldol reaction. We've learned that an alpha beta unsaturated carbonyl compound can also come from an aldol reaction, but an aldol reaction with dehydration. We've now seen that a 1,5-dicarbonyl compound can come from a Michael addition reaction. And now we're going to see two more, one in this lecture and one in the next lecture. So we're going to learn now that a cyclohexenone can come from a series of reactions that collectively are called a Robinson annulation. And in the next lecture, I'll show you that a 1,3-dicarbonyl itself can come from a reaction called a Claisen condensation. And with this little set of clues, with this knowledge of thinking backwards, when you see a molecule, even like this cyclohexenone, you say, oh, wait a second, that's a cyclohexenone. He just said it's coming from a reaction we're about to learn. When you look at ethyl acetoacetate, you say, oh, that's a 1,3-dicarbonyl compound. That can come from a reaction we're about to learn. So in many of these reactions, you can concatenate one after the next to build up products. When we started talking about ethyl acetoacetate, I said, oh, this is a molecule that comes from two ethyl acetates that have condensed together by a Claisen condensation. So it's sort of like being part of this little cognoscenti, understanding, okay, this is one of the ways that molecules, this is a set of ways that complex molecules can be built up from simpler molecules. So let's at this point dive in to the Robinson annulation reaction. Cyclohexenones are important molecules. They're often building blocks of complex natural products, of steroids, for example. Being able to synthesize these molecules provides access to medicines and drugs like cortisone, which is used for inflammation, and steroids that are used for birth control pills and the like. And so the discovery of a reaction that forms cyclohexenones from much simpler components, bringing together a 4-carbon component and a 2-carbon component to make a 6-membered ring, won the Nobel Prize for Robert Robinson in 1947. Let's take a look at an example of this Nobel Prize winning reaction. So if I take this carbonyl compound, and in general, we can say a ketone or 1,3-dicarbonyl compound. And we combine it, we mix it with an alpha beta unsaturated ketone. This particular molecule here is called methyl vinyl ketone commonly. In the presence of a base, let's say, I'll forget about heat here. We may warm this up, but let's just say a base such as sodium hydroxide and water, or sodium ethoxide in ethanol, or sometimes sodium hydroxide and ethanol water mixtures. We get a cyclohexenone product. And if you look at this reaction for a second, I think I would say, wow. I mean, I would look at this and say, what the heck? How did that occur? And that's probably why this reaction, one of the reasons this reaction resulted in the Nobel Prize, in addition to it being incredibly useful. Because what happens all on its own is a cascade of different reactions, all occurring in sequence. Everything in this reaction mixture is in equilibrium, and yet we go down a pathway to generate a single product, at least as the predominant product. And this cascade of reactions involves 3 sets of reactions, which is what we've sort of been laying the stage for here. It involves a Michael addition, Michael reaction, you can call it either, then an Aldol reaction, and then a dehydration. And I always think this is a little bit crazy, right? We get all these reactions occurring as a cascade. This is mad. It's a good way to remember it in terms of what's happening. So let's take a look at the various steps. I don't want to write this out in painstaking details with curved arrows. We've done this for all the steps. We've written at points curved arrows for enolate formation, curved arrows for aldol reaction, curved arrows for dehydration, and so forth. So I just want to write out the key intermediates here, and hopefully you'll be able to see. Okay, so the cyclohexane dione molecule on the left, 2-methyl 1,3-cyclohexane dione, in the presence of base, remember, this is a 1,3-dicarbonyl compound. It's relatively acidic. I said the pK of a 1,3-diketone is about 9. In other words, it's deprotonated by sodium hydroxide, pK of water about 15.7 or 16. So we can imagine that we form the enolate all in this mixture, like so. And if you're having trouble because I know we're doing a lot, although I don't like to write just the minor, just a minor resonance structure. If you're having trouble thinking, you can say, okay, I can at least hold in my head, maybe with the help of a little bit of paper, the minor resonance structure. Now, this enolate can add to the beta position of the alpha beta unsaturated ketone, of the methyl vinyl ketone. And again, I don't want to push curved arrows here because I think you've had all the skills that you need to do so. But I do want to write the intermediates because it is a lot to take in the first time around. And so you can practically picture in your mind's eye the alpha position of the 1,3-dicarbonyl compound enolate attacking the beta position of the methyl vinyl ketone. Can you see that? Can you see how we go ahead and in doing that, we now form this bond? And in sodium hydroxide and water and aqueous base, protons come on, protons go off. The enolate is in equilibrium with the corresponding ketone. And so I will go ahead and write that next intermediate in this cascade of reactions. So I'm getting ahead of myself here. All right, so that's our Michael addition step. Let's take a look at our aldol. So in these conditions, protons come on, protons go off, every enolizable position. I guess I should say protons come off, protons go on. And so we also form an equilibrium concentration of this enolate. And I've written this enolate in a very suggestive conformation where you practically can see it poised to form a six-membered ring. In other words, the carbon of the enolate is able to attack the carbonyl of the cyclohexane dione to form a six-membered ring. And so I'll write our next intermediate, our aldolate. And again, hopefully, if you were following with me, you'd be able to write the curved arrows to represent this. And in basic conditions, protons come on, protons go off. And so the aldolate, as we've seen in our aldol reactions, the aldolate can protonate like so to generate our aldol product. Basic conditions, protons come off, protons go on. Under these equilibrating conditions, one of the many enolates that forms transiently is this enolate. Tidy up my bond here. It's whoops, a little bit messy. iPad, ever helpful. Tried to get rid of a bond. Okay. And now you can see how we're set up for the dehydration reaction. If you need a little help, I can do that. The enolate pushes down, you push out hydroxide like so. And that gets us to the cyclohexenone product, to our Robinson annulation product. Thoughts or questions? So the Robinson reaction, Robinson annulation, is a little bit of a finicky reaction. In other words, it does take the right conditions, choice of conditions, in some case, the right carbonyl compounds to make the reaction occur. 1,3-dicarbonyl compounds are particularly good in the Robinson annulation. And so I'll just show yet another example so we get a little bit of a feeling of the diversity of this reaction. So another alpha beta unsaturated ketone. So methyl vinyl ketone is 3-butene 2-one. Here I've chosen let's see, 2-pentene 3-one, but regardless of the name, if we take this and we take our alpha beta unsaturated carbonyl and we take our 1,3-dicarbonyl, doesn't have to be a 1,3-dicarbonyl, and cook it up in sodium ethoxide in ethanol. All right, so the reason I give this example here is both for us to see the diversity of chemistry, but also to start to learn how to see a Robinson annulation. In short, how to do a retrosynthetic analysis. So the first thing you'd look at and say is, oh, this is a cyclohexenone. That's a clue that this molecule could form by a Robinson annulation. And you'd be able to take that apart in your mind's eye if you can picture it. If you can picture that the last two steps of the Robinson annulation were an aldol reaction and a dehydration, just a second, we would say, we can form that bond. In other words, this part on the left would be a carbonyl group, and this part on the right would have been our enolate. If we look some more, we'd say, okay, and then I can picture now that we can form this bond. In other words, I would say, all right, by way of retrosynthetic analysis, if I can picture the formation of our cyclohexenone, I can picture it going back to this carbonyl compound and this alpha beta unsaturated carbonyl compound. And as you work through additional examples in the textbook, you'll get even better at recognizing this reaction and figuring out how to do Robinson annulations. We had a question. The substituent between the two 6-membered rings in this particular example was here, carboethoxy group. I'll write this nice and big. And remember, of course, carboethoxy group is just one of several ways of writing this. You can write it like this. You can write it as COOET, as I just did. You can write it as CO2ET. Chemists tend to use all of these notations interchangeably, just how convenience and space tends to dictate. Other questions? So in our retrosynthetic analysis, I'll just sort of point out that this is the A and the D, and this is the M in our thinking. All right, let us now try one example, see if we're able to apply this sort of thinking. So we'll take a really complex molecule, and I'll write this as follows. Synthesize the following from simpler components. So let me draw a tricyclic molecule, and we'll put in what we'll call the C ring of it. We'll make it aromatic and have a benzene ring, and we'll call the next ring the B ring, and that's a cyclohexane ring. The next ring like this. And obviously, at this point, you're all primed for Robinson annulation. In other words, we've just been talking about this. I've just said, oh, look for these features. And you'd say, we have in the A ring of this molecule a cyclohexenone. I can see the double bond. I can see the carbonyl. And I just learned this retrosynthetic analysis. I just learned this way of thinking about this, where this bond corresponds to the aldol and dehydration steps, and this bond corresponds to the Michael addition step. And so with a little bit of practice, you can go ahead and say, okay, now I have the skills to take this molecule apart retrosynthetically and think about the components from which it can be made. And that double bond is now a ketone that became a double bond in the aldol and dehydration. And the other component is now the same ketone, the pentanone that we saw above. If you have trouble seeing it over here, you could just say, okay, I could write it in this orientation over here and then sort of see everything poised for the Michael reaction. And so remember, this retrosynthetic analysis, this process of thinking backwards, is not an answer in itself. It's the thought process. So let's now go ahead and answer the question, synthesize this tricyclic molecule from simpler components. And we'd say, okay, I will start with this ketone. I will mix it with this enone. I will combine them in the presence of some aqueous, some base, sodium hydroxide, and ethanol. I'm actually taking a real set of conditions that were used here. If you'd say, oh, but he always tells me I like to match sodium ethoxide with ethanol, you could say sodium ethoxide. Sodium hydroxide, of course, is convenient here. It does no harm. It hydrolyzes no esters, and I can go to the chemical shelf and grab a 1 pound bottle of it. Anyway, either way, and mixing these together, maybe heating them up a little bit, generates this product. I've focused on base catalyzed Robinson annulation, and this is the typical conditions. There are many, many variants. I will invite you a week from Tuesday to attend a lecture by Professor Dave McMillan, where you will learn about amine catalyzed reactions if you want to attend, or maybe you'll just learn about his winning the Nobel Prize and his passion for science. But I will show you one other set of conditions that sort of are congruent with what you've learned right now, and that's acid. And so I'll show you again a real set of reaction conditions. If we take 2-methylcyclohexanone and we take methyl vinyl ketone and we heat them up with a little bit of sulfuric acid, catalytic sulfuric acid, in benzene, we also get a Robinson annulation reaction to get a cyclohexanone. And you can picture many of the reactions occurring in an acid catalyzed manifold. You can picture, for example, the Michael addition reaction occurring in acid, not by way of the enolate, because you don't have any appreciable concentration of enolate, but by way of the enol, which forms in equilibrium. And although enols are not supernucleophilic, in acid, you'll have an equilibrium concentration of the protonated methyl vinyl ketone. And it can attack like so. To generate a new enol, we lose a proton, we tautomerize, rewrite that over here, meaning that the enol converts to the ketone, and when all is said and done, the first step of Michael, Aldol, and dehydration that constitute the Robinson annulation occurs. We can generate an acid, protons go on and protons come off. We can tautomerize, we can protonate, we can get an enol. That enol is again poised to attack the protonated carbonyl group. Like so. You can lose a proton. Get to the aldol product. And finally, in acid catalyzed conditions, we can again protonate the carbonyl, protonate the hydroxy group. We can lose a proton. And we can lose, lose H2O to get a carbocation, and we can lose a proton to get the enone. So in practice, the Robinson annulation can be a little bit tricky, can be a little bit low yielding. Often people will try several sets of conditions to get a decent yield. That yield might be 40%, it might be 60%. Sometimes it's higher. But here's an example of another manifold, and I think it provides a good example of the diversity of carbonyl chemistry. So we're going to have our exam next. Of course, that's going to draw upon everything, your textbook, your homework problems, the contents of the class, spectroscopy, nomenclature may appear on it. I wish you all tremendous success, and we'll look forward to seeing you on Thursday. Thank you very much. Have a good time today and tomorrow. Take care.